Good morning, quantum enthusiasts. It's very lucky that it's just you here. We're going to have a drawing for sure today, so like the fewer people that show up, the better it is for you all. Today's probably maybe my favorite lecture, one of my favorite lectures. I really like it. We're going to talk about this CH-SH game and the nature of reality. Okay, so last time we studied a lot this very famous entangled two-qubit state called EPR state. And EPR, I'll tell you now, stands for Einstein, Podolsky, and Rosen, three physicists. And it's named after them because they wrote a paper in 1935 where they basically were expressing their feelings that the laws of quantum mechanics, as were known at the time, which are still the laws of quantum mechanics today, were incomplete. So they weren't sure what the fix is, but they felt that there was a problem. So why did they think there was a problem? I'll try to explain it. I don't fully understand what their beef is, and we kind of now know that they were wrong, but I'll try to explain what they were thinking to the extent that I understand it. So they felt the following fact, which seems fine, that any physical experiment you do in the world at some physical location, called the location L, the outcome of that experiment should be determined by some real thing, some real physical thing that's at L, or like in the vicinity of L. Okay, and I guess this belief is called local realism, like local meaning like it has to be, the outcome has to be determined by stuff at L, and real meaning, I guess, some real thing that's at L. And that seems pretty reasonable. It's kind of like if you were trying to program the universe, like the physics engine for the universe, it should be that like all the information you need to know to explain what's going to happen at L is stored at or around L. Seems sort of reasonable. Now this seems to be violated by the laws of quantum mechanics that we've been using throughout the course, which dictate that, for example, Alice and Bob can get together and make two qubits, A and B, in this state, and then Alice can walk really far away, and Bob can walk really far away, each with their own qubit. And it would seem, from our point of view, that nature has to remember that like there's this electron over here and this other electron way far apart that have some joint relationship between them. And yeah, Einstein, Podolsky, and Rosen didn't like that. Now, they had in mind, or one thing that was kind of upsetting of them was, well, this basic experiment, which you can, I think probably they could do it at the time, but they could certainly reason about it, which is this. So imagine Alice and Bob make two qubits A and B in this state, EPR. And as always, Alice picks up A, goes far away. Bob picks up B, goes far away. And then let's say Alice measures her qubit A. Well, you can see there's like going to be a 50% chance she gets 0 and a 50% chance she gets 1. And then when she sees it, let's say she sees 0, she instantly knows that Bob's qubit is now just in the state 0. And therefore, when Bob measures, he'll definitely see 0. So she sees 0 and she like instantly knows, oh, now Bob will also see 0. And similarly for 1. Now, they agreed that this would happen, and they weren't upset by this or anything. They thought that's fine. And they were right to be not upset, because this is actually not a weird scenario at all. This scenario is, I mean, the same thing would seem to happen if you consider this purely classical code. So let's look at this purely classical code. Imagine, like, I don't know, Alice and Bob get together in a room with like a normal computer, and they set A to be a random bit, and they set B to also equal A. So now A and B are either both 0 or they're both 1, 50-50 chance. But like that's inside the computer. And then like Alice takes, the microchip or the RAM chip that has A on it in her pocket, and she doesn't look at A yet. And Bob takes the classical bit without looking at it yet, and then they go far away. And then Alice says okay, now is the time I'm going to look at the bit. And she's like sees 0, let's say. Then she also instantly knows that Bob has 0, and when he looks at his bit, he'll see 0. And conversely. Okay? I like the version with gloves, where like Alice and Bob like get together with like a package of gloves, and then they like both like take one without looking, and then they travel far away. And then if Alice looks at her glove and she sees the left glove, then she instantly knows, oh, Bob has the right glove. So that's not weird. But I guess like Einstein, Podolsky, Rosen's position was that like underlying quantum mechanics, it's maybe not the rules that I've told you in this class. It must be that somehow when Alice and Bob separate these two particles A and B, it must be that they're like secretly measured, and like it's at that moment they kind of, the randomness happens and they decide to either both be 0 or both be 1 when they get measured. So they kind of, I guess, would feel that it must secretly be like this, is what's actually happening. And like the decision about what the measurement outcomes is going to be has been made at this point. Whereas the way I tell it, I mean, and the way orthodox quantum mechanics goes is, it hasn't yet been decided whether they'll both be A or both be 0 or both be 1 until like one of them actually gets measured, which could happen much later and far apart. So they thought quantum mechanics must be incomplete, and we'll eventually figure out some more rules that'll make this look more like this. But they were wrong. So in 1964, this guy, Scottish physicist called John Bell, thought of like a new experiment that was like, started like this, but was like a bit more complicated, which had the property that if it were performed, it would sort of prove that physics cannot have this local realism property. That it cannot be like EPR expected, and it really must be like how I've told you quantum mechanics is, where you have these far apart particles that nature needs to remember are in a joint state. And his like version of it was like kind of complicated, and then like 4 years later in 1969, these 4 people called Clauser, Holt, Shimony, and Horner, maybe it's Horner and Holt, they gave like a much simpler and clearer version of this experiment, which is now called the CH-SH game. Or I like to think about it as the red, orange, yellow, green game. And that's what we're going to talk about in this class. So sort of a quantum mechanics experiment that sort of proves that these counterintuitive laws of quantum mechanics are true. Okay, so to get to it, let's recall from last time that if you have 2 qubits, so that's one thing to recall. If qubits A and B are in any state at all, so any state at all is defined by 4 amplitudes, and last time we were talking about arranging those 4 amplitudes into a square and then even thinking of that square as a matrix. So any state could be vec M, if you remember this notation, where M is a 2x2 matrix. And you do U, which is a 1 qubit operation on A, then the new state is vec of U times M. Or, alternatively, if you start from this state and then do V on B, the new state is vec of M times V transpose. Okay, and this is really just like an accounting trick. It's like a way to like make the transformation of amplitudes writable in a very succinct way. Okay, so it wasn't anything new that we hadn't done already in lecture 5, just like a succinct way of writing it. Okay, so let's follow up on this. In fact, we talked about some consequences of this last time. So say the initial state of A and B is EPR. And that, by the way, I mean, one reason it's very interesting is that's the vec of the 2x2 identity matrix. You know, the 4 amplitudes are 1, 0, 0, and 1. You know, they're 1, 0, and 0 are omitted, and then 1. Okay, and say Alice does, well, our favorite, 1 qubit operations by now are rotations. So let's say she does rotate by alpha angle on A for some angle A. Sorry, alpha. And let's say Bob also, he owns qubit B. He does rotation by some other angle, beta, on B for some angle beta. So the question is, what is the new state? Okay, and this is going to be easy to answer based on what we know here. Let me just mention that, because they're operating on separate qubits, it should be the case that it doesn't matter in which order they do these 2 operations. They could do them Alice first, Bob first, simultaneously. Shouldn't matter. Okay, well, the answer, I claim, and we'll just double check it, is that it's vec of, well, we don't have to double check, it kind of follows immediately from this. The rotation matrix, this 2x2 rotation matrix, times the identity times the transpose of rotate by beta. Okay, and that follows from these two facts immediately. And actually now you kind of do see that it doesn't matter the order in which they do them, because like if Alice went first and Bob went next, it'd be like you put the parentheses here. And if Bob went first and Alice went next, it would be like you put the parentheses here, but we know that in matrix multiplication it doesn't matter where you put the parentheses. So now we might think to ourselves, okay, what is the transpose of the rotation matrix? These are real matrices, so this is the same as if I put the dagger, and we know that this is unitary, so this transposition is just the undo of rod B of beta. And the undo of rotating by beta is rotating by negative beta. And then multiplying by the identity matrix doesn't do anything. And now we can also observe to ourselves, so this I goes away. What do you get if you do rot alpha times rot negative beta? Well, this is the action of rotating by negative beta, and this is the action of rotating by alpha. So if you do those consecutively, the result is to rotate by alpha minus beta. Okay, and so that's the answer. Okay. All right. So this is a state. This is a 2-qubit state with 4 amplitudes. I won't write them out, but that Alice and Bob can get EPR into by doing, rotations on their own qubits. And you can see this is kind of like this little competition, like Alice can do some rotations, Bob can do some rotations. It doesn't really matter the order. They eventually get into a state which is of this form, like the vectorization of some rotation matrix. So these kind of 2-qubit states are very, very similar to EPR states. I kind of think of them as like, they're all like cousins. And so we're going to have some notation for them as well. Like I said, they're sort of variants of the EPR state, this state. So let's make some notation. I'm going to define a new 2-qubit state called EPR sub theta, where theta is any angle, to be the vec of the rotate by theta unitary. Okay, and now I'll write it all out. So this is, if you remember, this rotation matrix is cos theta minus sine theta, cos theta. Okay, because this column is where 1, 0 rotates to, and this column is where 0, 1 rotates to. Okay, and so that, just to remind you, that means that it's this 4-qubit state, cos theta, amplitude on 0, 0, minus sine theta, amplitude on 0, 1, plus sine theta, amplitude on 1, 0, plus cos theta, amplitude on 1, 1. Okay, so it's the same 4 numbers, like arranged like this. Let me write it like this, plus negative, plus. Okay, so you see the 4 parenthesized numbers there. In particular, rotating by 0 degrees is the same as doing nothing, which is the identity matrix. So in this notation, like EPR sub 0 is just the same as good old EPR. Okay, fine. So here we thought about what would happen if you start an EPR and then Alice starts doing rotation on her qubit, Bob starts doing rotation on his qubit. Let's think about now if you start in this kind of state and they start doing rotations. So let's say, as a question, say these 2 qubits, A and B, are now in state EPR sub theta. And Alice does let's say rod, let me just not be confusing, I'll call it alpha prime on A. Okay, so what's the new state? And, well, the starting state is vec of rod theta, so we can just use this rule again. It's just like you multiply the matrix on the left by the operation Alice did, so it's vec of rod alpha prime dot rod, well, times, I should say, rod theta. And again, like, this is a 2 by 2 matrix multiplied. This is the action of rotating by theta. This is the action of rotating by alpha prime. So when you do them consecutively, it's rotation by theta plus alpha prime. Maybe it would have been more natural if I wrote alpha prime plus theta, but it's the same. And therefore, the answer in our notation is EPR theta plus alpha prime. Okay, so if you're in this joint state, Alice does rotation alpha prime on her qubit, you get to this new joint state where, like, the angle added in here. And it would be just the same for, well, almost just the same for Bob. I realize now I have a little typo in my notes. If Bob instead did, rod beta prime, then we'd have to multiply on the right by the undo of this, which is rod like negative beta prime. So we'd get to EPR theta minus beta prime. Okay. So I have this weird, like, mental model. I don't know if this will help anybody. I have this, like, weird mental model of these family of states, EPR theta, is kind of like a joint steering wheel. Like, somehow you got this, like, steering wheel, and, like, I don't know, for a car or a pirate ship or whatever, and, like, it has, like, a pointer on it. This is just, and, like, this angle is theta. This has no mathematical meaning. It's just some weird mental image I have. And, like, it's like Alice and Bob, like, both have their hands on the steering wheel. Like, here's, like, Alice's hand. I don't know if she has the correct number of fingers. Bob's hand is like this. And they can, like, jointly manipulate this, like, steering wheel. So, like, Alice says, like, I'm going to rotate by alpha, and she does that. And, like, this theta pointer, like, gets alpha added to it. But Bob's holding it with, like, his other hand, and, like, he's like, I'm going to rotate my qubit by beta. And, like, that pulls the joint angle by beta in the other direction. Okay, so this is, I mean, maybe how you can imagine this funny 2-qubit state. Okay. So now, this is very important. What happens when Alice and Bob measure their qubits or do extract on their qubits? This will be pretty interesting. So we're going to work that out and then save it in our minds because it's very important. Okay, so let's say what happens if you do extract all 2 of them on 2 qubits that are in this state EPR theta. And again, we saw a couple lectures ago, if you do extract all, it's really, you can think of it as Alice does extract privately on her qubit, then Bob does extract privately on his qubit, or the other way around, or they're simultaneous. It doesn't really matter. They can do them on separate qubits. So we'll just work it out by working out what happens when you do it in our most old-fashioned like way where we just do extract all. Now, the first thing to remember is, let's work out the answer here. First thing to note is this EPR state is unnormalized. I made it this way because I like it. Otherwise, there's like all these square root halves floating around. So we should first figure out the total squared amplitude. Does somebody want to tell me the total squared amplitude? Yeah, 2, yeah. Because, well, here are the amplitudes. We get cos squared, and then we get sine squared, and then we're like, oh, that adds up to 1, right? Cos squared plus sine squared is 1. And then we get also sine squared and cos squared, so that's another 1, so that's 2. Okay, so the total squared amplitude is 2. Therefore, like, the probabilities of seeing the 4 outcomes is not just the amplitude squared, it's the amplitude squared divided by 2. Okay. I am now going to make, the ultimate chart that we'll definitely want to remember. Try to never erase this. So let's draw a chart here. This is just the measurement outcome chart. Okay, Alice can see either 0 or 1. Bob can see either 0 or 1. So this is 0, 0, 0, 1, 1, 0, 1, 1, as always. And we'll just work out the probabilities. So for 0, 0, it's cosine theta squared. Well, but we got to divide by 2, so a half. And for 1, it's the square of 0, 1, it's the square of negative sine theta. So the negative doesn't matter, and we just get sine theta squared here, also times a half. And this one is also sine theta squared. And this one is cos theta squared. Okay, so this little 2x2 table tells you the 4 probabilities of getting 0, 0, 0, 1, 1, 0, and 1, 1 when they jointly measure. These 4 numbers are positive numbers that add up to 1, so everything makes sense. And I would really like you to put you in mind of, like, you know, maybe when you first took probability and they're trying to illustrate things like, oh, you can have 2 random variables that are independent, or maybe they're positively correlated, or maybe they're negatively correlated. Definitely think a lot about that. We're going to talk about it just now. So the measurement outcomes of Alice and Bob are like this. Actually, let's think for a second, just what is the probability that Alice sees 0? As I erase the board, you can figure that out. And also maybe figure out the probability that Bob will see 0. Okay, so work it here. The probability Alice sees 0 is, 1/2, yeah. It's just the sum of these two numbers. The sum of these two numbers. This is Alice seeing 0. It's a half cos theta squared plus a half sine theta squared, so we get a half. Cos squared plus sine squared is 1, so it's a half. And similarly, the probability that Bob sees 0 is half. So I should also have said, like, probability Alice sees 1 is also a half. Probability that Bob sees 1 is also a half. So individually, what Alice sees is a coin flip, 50-50. Also, individually, what Bob sees is a coin flip, 50-50. And it doesn't matter what theta was, no matter where the steering wheel is pointing, if Alice measures, she'll just see 50-50, 0, 1. And same for Bob. But it's not like they're independent coin flips. That's kind of the point. And to understand the kind of nature of the correlation, let me just say, let's work out what is the probability that the Alice outcome is the same as the Bob outcome. Well, I'll just won't make you say it. Probably the same is like this entry plus this entry. So it's the square of cosine theta. And the probability, well, we know that the probability of the A outcome doesn't equal the Bob outcome. Well, it's 1 minus this, or it's, this plus this. So it's the square of sine theta. Oh, let's pass this out, by the way. Get started. Okay, so let me just write that over here because we'll want it later. Probability is same equals cosine theta squared. And diff is sine theta squared. Okay, so these are 2 random bits, but they're not independent random bits. These are correlated 50-50, albeit correlated random bits. And what's interesting is the correlation is a function of theta, and theta is something that Alice and Bob can control by doing rotations on their qubits. So somehow they have these qubits, and they can like do some rotations to try to affect the correlation of the outcomes that they see when they measure. Let's just do a couple of special cases to have special cases in mind. So for example, measuring, good old EPR, which is EPR 0. Well, we could just think about it because EPR itself is very simple. It's just ket 0, 0 plus ket 1, 1. But from this point of view, theta is now 0. So cosine of 0 is 1, and sine of 0 is 0. So in this case, the bits are like perfectly like, I don't know, fully correlated. They're always the same. So they're 50-50, but they're also always the same. And we know that, right? Like if Alice measures in EPR, she sees 0 50% of the time, 1 50% of the time, and for sure Bob will see the same thing. Okay, alternatively, if you measure EPR 90 degrees, then, okay, theta is 90 degrees, cosine of 90 degrees is 0, sine of 90 degrees is 1. So it's like they're always different. So the bits are sort of fully anti-correlated. Okay, and I guess, by the way, this example, maybe I'll annotate this. When cos is 90 degrees, like this is a 0, 1, 0, 1, 0. So in that case, the state is negative 0, 1 plus 1, 1. Oh, plus 1, 0. And so again, you can hopefully easily see that whatever Alice's measurement outcome is, Bob's will for sure be the opposite. And then there's a case in the middle, like if they somehow get the angle to be 45 degrees, then this is a half, this is a half, so it's like independent random coin flips. They're 50-50 that they'll equal each other. So these are like independent random bits. Okay, and that's the thing that's like truly unusual and fascinating about this scenario is that when they start out with this EPR state, they can control the amount of correlation. They can kind of jointly control the amount of correlation they'll see when they measure. And so that kind of crazy ability is exactly what's exploited in this CHSH game or experiment that I'm going to talk about now, which kind of defeats Einstein, Podolsky, and Rosen's theories.